Here we have the chart that actually has the real numbers, because I realized in the last video I said 1.8 instead of 1.7, but this chart does have the real numbers that we will be using in this class to determine bond character. So again, if the electronegativity difference is greater than 1.7, you're going to have an ionic bond. If it's between 0.4 and 1.7, you'll have a covalent bond. And if it is less than 0.4, you're going to have a nonpolar covalent bond. So remember, this is a relative scale. Anything in science, anything in chem, there are exceptions to the rules. It's just a general guideline to follow. Some things follow different rules, but if you look at the differences down here, following the chart, you can see that ionic bonds have the bigger difference between the electronegativities, and as those get smaller, you end up having covalent bonds. If you have to write anything else in, take a pause. So how do we use those numbers? Well, you have the periodic table that has the electronegativity values on it, and that's what you're going to refer to. So if I want to know what the bond character is between hydrogen and chlorine, I would look at that periodic table that has their numbers. So hydrogen's electronegativity value is 2.2, and chlorine's is 3.16. We want the absolute value of the difference, so just take the bigger number and subtract the smaller number in this instance. So 3.16 minus 2.20 is 0.96. So then I have to refer to the table that we just looked at on the previous slide and go, well, what type of bond is this? 0.96 is between 0.4 and 1.7, so that would be a polar covalent bond. And that means that the one that has the higher electronegativity value to start, which was chlorine, will hold on to those electrons more than the hydrogen will. So if I were to draw an arrow to show the direction the electrons are going to be, they're going to be pointing toward that chlorine. Right here you've got some of these symbols here. You may have seen me draw these now and then on the board. These little symbols here just mean slightly. So the chlorine in this bond has a slightly negative charge, while the hydrogen has a slightly positive charge. If you need to fill anything else in, take a pause. Your goal here is to try to determine the bond character of the different bonds listed. So take a minute and do that on your own, and then when you're done, we'll come back. So the first one we're going to look at is sodium and chlorine. We already know this one's an ionic bond because we have a metal and a non-metal, but we can prove it by using those bond characters. So if I look at that periodic table that you should have in your packet, sodium's electronegativity value is 0.93. Chlorine's value is going to be 3.16. So if I took the difference between those two, I would get about 2.23. This means I have an ionic bond. So if I follow through on the rest of these, the difference between each of them for number 2 is 0.4. So that is going to be barely, but it still is a polar bond. Bromine and bromine, being the same element, will have the same electronegativity value to start, which means the difference between those has got to be 0, so this is just nonpolar. So it's just a nonpolar covalent. Sorry, I forgot that word. Carbon and hydrogen, the difference is 0.35. That gets me another nonpolar covalent. And between phosphorus and chlorine is 0.97, which is a polar covalent bond. If you got those right, good job. So we've walked through how we determine whether the bond itself is a polar bond. So that's the electronegativity difference between the atoms participating in the bond. And one of the atoms pulls the electrons toward it just a little bit more than the other atom gets it. So you get those dipoles, slightly positive and slightly negative ends to the bond. So what does that mean about our molecules and their shapes and their properties? So if I want to talk about a molecule, like water, being a polar molecule, well, then I've got to figure out, well, are the electrons in all of these bonds being pulled in one direction in general? So not just within one bond, but with all the bonds going on in that molecule. So what's going to happen here is if I've got a molecule that has polar bonds that are asymmetrically arranged, so this is where it comes in handy knowing your shapes and drawing them properly on paper. So it's going to be the arrangement of those polar molecules, the polar bonds, that's going to determine whether or not you have a polar molecule. And one thing to keep in mind down here is that you cannot have a polar molecule unless you have polar bonds. So if none of the bonds involved in that molecule you're looking at are polar bonds, then your molecule can't be polar. So that's another good way to start ruling some things out. Take a pause if you need it. As I was just saying, if I have only nonpolar bonds in my molecule, I can only have a nonpolar molecule. So something like chlorine bonded with chlorine is a nonpolar bond, which means the molecule it forms, so chlorine gas, would also have to be a nonpolar molecule. But if I do have polar bonds within my molecule, that means one of two things, that I either have a polar molecule or a nonpolar molecule, and I have to decide how by drawing out my modified Lewis structures and then adding a little bit to it. So we have to apply bond polarity to the shape of the molecule to determine if the molecule is polar. So we're tying it all together here. Again, a word I've thrown around a few times, a dipole. So if a polar molecule is forming, I will have what we call a dipole. So almost like a magnet, I have a molecule, so I guess we can do water here. I have a molecule that the oxygen here gets the slightly negative charge, while the hydrogens are slightly positive, so it's almost like ends of the magnet. You have the north and south end. I have the negative end of my molecule and the positive end of my molecule. If you need to pause, take a second. So if you're a step-by-step kind of person, here are your steps to determine whether or not your molecule is a polar molecule. So the first step that we've been working on in general is to completely finish the modified Lewis structure and determine its shape using that Vesper theory we talked about, so that table you filled out on the last set of notes. Then you're going to look at every individual bond that you have in that molecule and determine the difference in electronegativity. If any of those bonds are polar, you're going to draw what we call a vector line that points toward the more electronegative atom. So between hydrogen and chlorine, this is a polar bond, and since chlorine's electronegativity is higher than that of hydrogen's, I draw this vector line right here, above or below, usually above the line, so don't make it part of the bond, but above it, and draw an arrow pointing toward your more electronegative atom. So if the molecule overall has arrows all pointing at the same place, well, then I have what we would consider to be a polar molecule. If they all tug of war equal in opposite directions, then I would have a nonpolar molecule. So looking at a few examples here, we have a molecule here with carbon, hydrogen, and chlorine, and then one with just carbon and chlorine. So carbon's going to be the center atom. There's only one of it. It tends to take the center. Again, little things to watch for. We know that hydrogen is always terminal, and my chlorines only being able to make one bond each, also going to end up being terminal in this instance. So what I need to do is take a look at their individual electronegativity values, where carbon had, let's see, I can write it here. Carbon's electronegativity is 2.25, chlorine's was at 3.16, and hydrogen's was 2.20. So I would go and do the difference between the bonds here, and it would say, okay, well, the difference between carbon and chlorine is within that polar range. So those bonds are polar. The carbon-hydrogen bond, however, is not polar. So if I'm going to draw my vector lines in red first, chlorine's more electronegative. It's pulling those electrons toward it. And that'll happen on each individual bond, just like you see in the picture. So these two guys essentially cancel one another out. It's like a tug of war. So if that were it, if those were the only two polar bonds in this molecule, then this would not be a polar molecule. But because I have this chlorine down here pulling without this hydrogen being able to pull back, that means that I do have a directional dipole here, because this chlorine is going to tug some of the electrons toward it without anything else to pull it back. So again, almost like a tug of war. So this would be a polar molecule. If I'm looking at the carbon tetrachloride, again, all of these bonds are polar bonds, which I have drawn with the red arrows here. And they're all pulling in equal opposite directions this time. So each chlorine has something else pulling against it in the opposite direction. So because that is the same for each one of these, they essentially cancel out, and I have polar bonds, and all of the bonds are polar, but my molecule is nonpolar. So those are the things where getting the shape correct is important. So this shape is fine for the tetrahedral, but it really is that trigonal planar that is the one you need to watch out for. So here's one for you to take a try of the phosphorus trichloride here. Your goal is to first figure out the Lewis structure, then calculate the bonds, so whether or not they're polar, and draw any vector lines that might be needed. And then, if you've got a polar molecule, tell me, is it polar or nonpolar? And then draw in your big polar line, your big polar arrow. So looking at the electronegativities, phosphorus, sorry, I guess I should start at the beginning. Phosphorus is going to be your middle atom. It had those 5 valence electrons, 1, 2, 3, 4, 5. And there were 3 chlorines, so obviously phosphorus was going to be your center atom. It made bonds with the chlorines, as we have pictured here. Again, you can try to draw it a little bit more true to life or not. It'll still work for this trigonal pyramidal shape here, because they have the 1 lone pair, 3 shared pairs. But the electronegativity difference between the bonds is 3.16 minus 2.19, so my difference is 0.97, so all of those bonds are polar, meaning I have tug or pull going toward my chlorine on each of those bonds being made. Now, the ones that are left and right of one another essentially cancel out. Same here, right? They're equal but opposite directions, so they almost tug of war and just get stuck. But with the lone pair being at the top and there being nothing else to pull back, I do have an overall pull going down toward that chlorine, which we have also pictured over here. So this would also be a polar molecule. That'll be it for this section of notes. The next section is going to deal with hydrocarbons, and it's almost a little taste of organic chemistry.